All right, I'm going to talk today about the variability in the subtropical circulation of the Atlantic Ocean. Basically, I wanted to show a schematic. These are the components of the circulation that I'm going to talk about. In red, we talk about the warm water upper level flow of the Gulf Stream through Florida Straits and then northward through the Atlantic. Now, part of that recirculates in the subtropical North Atlantic Ocean, goes southward, and part of it continues northward in the North Atlantic Current. And as this warm water goes northward, it loses heat to the atmosphere. It carries warm water into high northern latitudes, but it also loses heat to the atmosphere. And gradually it becomes denser and denser until it becomes so dense that it can sink and form bottom water, deep water, as indicated by this blue current. So this is cold, deep water coming back southward along the western boundary of the Americas, down through the Atlantic, and eventually it goes and fills the global ocean, the world's ocean, with deep water. Most of the deep water for the global oceans is made in the North Atlantic Ocean, in the Nordic seas, north of Iceland, and in the Labrador Sea between Greenland and Labrador. The effects, we can see the effects of this in terms of sea surface temperature distribution. Now, this is a sea surface temperature distribution in February, so it's winter time. And what you can see is in the high, I'm not going to really be able to use the pointer because I'll lose the pointer, but up beyond Norway, north of Norway, the waters are still 5 degrees centigrade in the middle of winter in February. So this warm water makes its way all the way up and around the northern part of beyond northern Scandinavia. In fact, I think when I was a schoolboy, we learned that Russia's only warm water port, clear ice-free port, was Murmansk, around on the other side of up in here. That was the only ice-free port year-round for the Soviet Union. So that's a result of the circulation of the North Atlantic Ocean. Sometimes we show that as a conveyor belt, and this shows the global elements of it. It's a schematic of the circulation. It's missing the recirculation of waters. It just shows the net northward flow of warm water through the Atlantic, and then the formation of cold, deep waters and their southward progression around the global ocean. So this schematic shows the influence of the Atlantic, the North Atlantic Ocean, on the global ocean circulation. Now, this conveyor belt, where warm upper waters go northward and cold, deep waters flow southward, carries an enormous amount of heat northward through the Atlantic Ocean. So this is the heat transport through the Atlantic Ocean, the northward heat transport. And you can see that on this latitude of 25 degrees north, which I'm going to concentrate today, it transports 1.3 petawatts of heat northward. Now, a petawatt is 10 to the 15th watts, and so that's 1.3 million gigawatts of heat, an enormous amount of heat. And effectively, the ocean circulation in this region, where it's cooling off, in this subtropical and subpolar North Atlantic, where it is giving up heat to the atmosphere, the ocean acts like a radiator, heating the winds that flow off the east coast of North America, let's say in winter at 0 degrees centigrade, and then those winds which come across the Atlantic picks up the temperatures. So when the winds arrive in Spain or in the United Kingdom or in France, they're 10 degrees warmer in winter than when they left. And that's the kind of effect that we get in Europe as associated with this Atlantic Ocean circulation. So I want to talk today about the elements of this circulation and then later on about the variability in the circulation. So the first component is the Gulf Stream flow. Now, the Gulf Stream flow we're going to talk mostly about how it flows through Florida Straits, and then it does continue northward. The Gulf Stream, I like to show the chart that it is basically a very old chart that Ben Franklin put together in 1770 of the Gulf Stream. And he was doing that for a very practical reason, in the sense that the mail packets that were going at that time from England to New York, the mail packets from England didn't know about the Gulf Stream, and they would fight this current. So they're coming here, across here, they would get in the Gulf Stream, and they would make no progress. And so basically they took about 1 week more to reach New York when going from England to New York than it did to go from New York to England. And so he would try to make this map to encourage the ships to go to kind of cut across, to stay on one side of the Gulf Stream and then shoot across directly rather than stemming against the current for a long time. So we've known about the Gulf Stream since 1770. It's really probably one of the oldest, it's probably the oldest known ocean current. Now in Florida Straits, so you can imagine on this side, on the western side, you're basically in Miami Beach. You're sitting on Miami Beach, and then this is the Bahamas on the other side. So it's only about 90 kilometers across Florida Straits. And the symptom that we've long measured is the temperatures. You can see these steeply sloping isotherms banked up against the western side, banked up against Florida. And that indicates a very strong current. And here's a picture of what the currents are. And you can see that this is 2 meters per second, or 4 knots of current there. So when you're swimming in Miami Beach, when I swim in Miami Beach, I get very nervous about this strong current that's just offshore, ready to sweep me down to New York if I'm not careful, if I go out too far. So I always stay very close on the beach in Miami. So that's what the Gulf Stream flow looks like, a very strong current. At 25 degrees north, it's in the Florida Straits between Bahamas and Miami. Now the second component that's perhaps less well known is the deep western boundary current, which flows really as a strong current along the western boundary of the North Atlantic at depths between about 1,000 and 5,000 meters. So that's, if you like, an undercurrent, not very visible. But it was discovered about 50 years ago by John Swallow and Val Worthington, who did an experiment here and put floats, what we call swallow floats, in the deep water. And they observed it to run southward along this coast. It's a concentrated current. If we look at the modern measurements of this, so this is a set of measurements off the Bahamas, east of Abaco Island. There was the group at the University of Miami, led by Bill Johns, has had a long interest in putting moorings in to measure this deep western boundary current. So here we see an Antilles current, a northward flow, which may be an extension, an offshore extension of the Gulf Stream, flowing northward here. But the striking thing is this deep flow within about 100 kilometers of the Bahama Islands, carries very strong flow of water southward. In fact, this undercurrent, this deep western boundary current off the Bahamas, has a bigger transport than the Florida Straits, than the Gulf Stream, which is little appreciated by scientists, and certainly not by the popular, in terms of the popular press. So this current, we estimate the size of this current is about 35 sparedrops of transport. Now, one sparedrop is 1 million cubic meters a second of flow. and it's what oceanographers typically use. To put it in context, the largest river flow in the world is the Amazon, and it has about 3/10 of a star drift, 0.3 star drifts. So this current is 100 times larger than the Amazon flow, and it's subsurface and it's deep. Now the Gulf Stream flow, we estimate, has a transport of about 30 to 32 star drifts. So the deep western boundary current is only slightly bigger than the Gulf Stream, but it is bigger, and I think that's a remarkable finding. And as I say, it's only been known about since 1957. The third component of this circulation that I wanted to talk about was the mid-ocean recirculation. So this water that goes north and some of it recirculates, this is a southward flow over the entire mid-ocean region. And that component is very difficult to measure. And traditionally, we measure that by going across on ships from leaving, say, from Miami and going east to the coast of Africa or into the Canary Islands, or alternatively, when I first met Professor Rozon was in 1992. We did this section leaving from the Canary Islands on board Hesperides in 1992. It was a celebration of Colon's 500th anniversary of his historic journey, and in fact, Colon did effectively take this same route. He knew about the trade winds. He went westward from the Canary Islands and discovered America. It would have been remarkable if he hadn't discovered America, but I think probably the key aspect is that he got back to tell the tale that he had landed, he had found land. So we've done this section 6 times now. It was first done in 1957, just after the deep western boundary current was discovered. Then in 1981 by Dean Remick and Carl Wunsch. 1992 was led by Gregorio Perea from Madrid on the Hesperides. 1998 was done by NOAA ship led by Molly Barringer. In 2004, Stuart Cunningham led the expedition, and recently Brian King led another occupation in 2010. I believe as part of the Malaspina expedition, the Spanish have done, in 2011, have done another section, but I have not seen the results of that. Now, when you make a section like this and analyze it, it was traditionally done using Nansen bottles. This is a photo of John Swallow, who invented the swallow float, discovered the deep western boundary current, but he was also a very good hydrographer. And so in 1957, this is the way we were sampling the ocean with Nansen bottles and reversing thermometers. These days, we use a CTD package. This shows it's connected to the ship by wire. It's got an instrument in it that measures conductivity, temperature, and depth. From depth, conductivity, temperature, and depth, we get salinity, temperature, and now it measures oxygen. And then it has these water bottles in the same way as before. It takes water samples on the way up. And so we lowered this, an instrument like this, about 100 times across the section, like this 25 North section. And then we go across the ocean, and we're sampling. This is the type of waters that we're sampling. And basically, we get a section. So this is the Bahamas on this side and Africa on this side. We get a temperature section across the ocean. And what you see on this section, what I see on this section, are sloping isotherms that in a sloping thermocline slope southward towards the west across the ocean, and using geostrophic balance, geostrophic dynamics, we can estimate the size of the flow the southward flow that's associated with this sloping thermocline. And so that's how we estimate the amount of recirculation across the ocean. So that's, just to show you, there's a comparable salinity plot. So these are from the CTD measurements. And then in terms of water sampling, we collect, the water is very valuable, so we collect in 10-liter bottles. We collect water from great depths throughout the Atlantic Ocean, from 5,000 meters up to the surface, and then we take water samples. So here, I believe this is for, well, Gabriel can correct me, I think it's alkalinity.
It's oxygen, well, alkalinity.
One or the other, but it is a set of samples that we take. We take all the water, we use up all the 10 liters, and then we make the analyses in the laboratory. To show you this is from the 2004 section. This is a plot of CFC 11, so it's a chlorofluorocarbon. And what we see in this is that most of the ocean has no chlorofluorocarbons. All of the eastern basin has very little in terms of the deep water. The CFCs have only been produced by man for about 50 years. And so where there are CFCs near the western boundary current indicates where the waters that have been most recently in contact with the atmosphere. There's no CFCs put directly into the ocean itself, but they are put into the atmosphere, and then where the deep water is formed, and sinks, it picks up CFCs from the atmosphere. And so a figure like this shows you that the most recently ventilated waters are near are in the deep western boundary current near the Bahamas. Again, we have CFC 12, so there are two chlorofluorocarbons that are traditionally measured. We also measure chlorofluorocarbon tetrachloride, which is a slightly older tracer, but you get the same results with each of the tracers that you actually get. The most recently ventilated water is in the deep western boundary current. There is, of course, CFCs coming down from the surface, so the CFCs going into the surface, and then they kind of slowly mix down. But the mixing is quite slow. That's another point. The deep western boundary current is what we would call an advective pathway from the high northern latitudes, whereas this is a diffusive pathway down through the thermocline, and the diffusion is much slower than the advection when you get far from the source. I've put in anthropogenic carbon. Pete Brown at the University of East Anglia has calculated anthropogenic carbon for each of the sections, 1992, 1998, and 2004, where the carbon measurements were made. And you can see that in terms of the anthropogenic carbon, so this is the carbon that man has put into the atmosphere, it's also primarily coming is being sequestered into the deep ocean, primarily by this deep western boundary current. Again, there is input at the surface that slowly diffuses down, but the dramatic influx of the carbon CO2 is again seen in the deep western boundary current. Now, about 10 years ago, started to be a worry among scientists, particularly, that the thermohaline circulation, or this conveyor belt circulation, might slow down. So I'm going to talk about the Atlantic as to what the variability is in this circulation. But the IPCC report in 2001, so that's 10 years ago, looked at the coupled climate models around the world. There are about 12 coupled climate models. And basically there was a consensus among the coupled climate models that this thermohaline circulation, or this conveyor belt, was going to slow down as a result of the CO2 being put into the atmosphere. So there started to be a worry about whether that was actually going to happen. Now, the second thing is that the models have been used to see what would happen to our climate if we shut down this thermohaline circulation. Now, you can do that in a model by pouring fresh water on the surface. So in a model, they poured fresh water on the surface of the northern Atlantic, maybe to simulate a huge melt of Greenland, to see what would happen. And then for 100 years, so you shut down the meridional overturning circulation. We're now going to talk about meridional overturning circulation, or MOC. You shut down the overturning circulation, and this is what sea surface temperature would look like, or air temperature would look like 100 years after you shut it down. And you can see that it is 14 degrees colder over Iceland than it is today in these model simulations, and more than 10 degrees colder over Britain, maybe 6 degrees colder over Spain. So it can have a large effect, at least in terms of model simulations, on the climate. And then helped, I suppose, by the film The Day After Tomorrow, which maybe you have seen, we convinced that we proposed and then convinced the governments of the United States and Britain and England to give us funding to monitor the meridional overturning circulation, or the MOC. So in 2002, we proposed to continuously monitor the circulation of the Atlantic, and we call that Project RAPID. Now, it involves a cooperation between the UK and the US. And the funding agencies are the Natural Environment Research Council here in England, National Science Foundation, and NOAA in the United States. And it was, in retrospect, we did it quite well. We proposed this jointly in the US and the UK, and each of us had a part playing. So the NOAA funding provided the Atlantic Oceanographic and Meteorological Laboratory in Miami to monitor the Florida Straits, the transport of the Gulf Stream through Florida Straits. National Science Foundation supported the University of Miami to monitor the deep western boundary current off the Bahamas. And then here in Southampton, NERC provided us with support to monitor the mid-ocean circulation and the overall overturning with support and supported by NERC. And so I want to talk now about the monitoring system and show you some of the results about the variability. So that's our schematic of what we're trying to monitor. We have the rapid array superimposed on the bottom. So we picked a latitude of 26 degrees north, where we go across the ocean at 26 degrees north, and we put a series of moorings, mostly on the western boundary and on the eastern boundary, with a few near the mid-Atlantic ridge. And this is how we try to monitor the components of the subtropical circulation, the circulation of the subtropical Atlantic Ocean. Basically, the way that the difficult part, I'll talk about that when I get to it. The first thing is that we want an effective way of monitoring the Gulf Stream transport through Florida Straits. Florida Straits is very difficult to keep moorings in, but we use an electromagnetic cable. It's an old telephone cable that goes from West Palm Beach to the Bahamas. And if you know your physics, the flow of a conducting fluid through the Earth's magnetic field gives rise to an ocean current. So on these cables, there's a shack in the Bahamas where we have recording equipment that monitors the voltage or the current in this cable, and the fluctuations in that current can be turned into the transport of the water. The stronger the transport, the more the current. But you have to also be monitoring the electromagnetic field, of course, at the same time. But just by monitoring this cable, we get a good estimate of the Gulf Stream transport through Florida Straits. So a remarkably easy measurement. We have had trouble we have a gap in the data in 2004, which is due to two hurricanes came. Actually, the first hurricane came and took the roof off the shack, so it started to rain on the equipment. So the equipment shut down, and the next hurricane took the shack away, and with the equipment. So we have a gap in the time series. But that's the major problem we have, is really to maintain the equipment monitoring the circulation. The second element here is that we have in the very surface layers, we have an Ekman transport, a wind-driven Ekman transport. And so over at this latitude of 26 degrees north, we have trade winds blowing from east to west across the ocean. And in terms of ocean dynamics, that wind stress, that westward wind stress, gives rise to a northward wind-driven surface Ekman transport. So it's to the right of the wind. And we can calculate, we can define the size of that wind-driven transport just by knowing the size of the wind stress and then using the Coriolis parameter at this latitude. We get Ekman transport. So we can monitor the Ekman transport just from knowing the winds. And in effect, the amount of northward flow across this latitude is quite easy to monitor. We monitor it with cable through Florida Straits here. This is a record going back to 1981 of Florida Straits transport. Gulf Stream transport through Florida Straits, the Ekman transport from winds going back to 1980. One could take that even further back, and then you can sum up the two. And this is effectively the variability in the northward flows across 26 degrees north, across the whole basin. And you can see the size of the Gulf Stream transport. The mean is 32 stardrops, and the standard deviation of the transport is about 3 stardrops. So about a 10% variability, root mean square variability of about 10%. The Ekman transport has a mean of only about 10% as large, 3.8 stardrops, but the standard deviation of the Ekman transport is more substantial. It's 50% the size of the mean, and in fact the Ekman transport can reverse. At times you see negative values, but it's all in all it's a slightly smaller number. So when we add the two together, we get a mean northward transport of 36 stardrops with a standard deviation of about 10% of that value. Now, so that's an estimate of the size of the net northward transport and its variability over time. The scale, it looks very variable, but you can see that it's always up there around 30, above 30 stardrops. So that's the northward transport. Now, the southward transport is the difficult part to do. So this is the component that until we started doing RAPID, it was widely thought that this component was impossible to monitor. Now, the way we've chosen to monitor that component, this southward transport, is that we basically make measurements at the eastern boundary and the western boundary in these moorings, and we're principally making temperature salinity and pressure measurements. The instruments primarily measure temperature, salinity, and pressure, from which we can estimate time series of the dynamic height and the geostrophic pressure gradient, from which we can get the northward flow, and effectively a zonally integrated or zonally average north-south flow from using just the boundary current measurements at the eastern boundary and the western boundary. So that's the way that we have chosen to do it. And for that, we need these moorings, and the reason for the moorings on near the mid-Atlantic ridge is that we're trying to separate into a western basin component and an eastern basin component. But in fact, they're not as necessary as the eastern boundary measurements and the western boundary measurements. Now, that if we look at what that involves, basically, we started the monitoring in March 2004. This is the schematic for the 2010 array. There are about 40 moorings that we're putting in at the moment. So there's a lot of instruments concentrated. These are all the western ones, and these are all the eastern ones, and then just a few in the middle of the ocean. So it's an enormous effort. I think we counted up the number of instruments. There are 200 instruments on this. We basically go out twice a year. I call it hard hat oceanography. It is operational. This is Stuart Cunningham, who leads the RAPID project. These are railway wheels that we use for anchors for the moorings, old railway wheels. Stack them together, they form the weight to hold the mooring down. And then this is the buoyancy that holds the moorings up. So if we go back and look, each of the moorings has an anchor at the bottom, and then buoyancy up towards the surface that holds up the mooring. And then there are instruments, up to 25 instruments are put on a mooring line, and to get vertical distribution of the temperature, primarily temperature and salinity. And in the western region, we also have current meters to measure directly the flow of the water and the deep western boundary current type flow. Basically, from these measurements, this is the first year of measurements from March 2004 to March 2005, we can actually get, this is what I call the thermocline recirculation, is shown in red. That's in terms of the definitions used here, that's the transport between the sea surface, and 800 meters depth. And so you can see the fluctuations in that thermocline recirculation, varying from about 24 spheredrips down to only about 7 spheredrips over the course of the year. So that gives you an idea. We are monitoring the slope of the thermocline and the geostrophic southward flow that's recirculating waters. We've divided up into the intermediate waters. There's a little bit of northward flow of Antarctic intermediate water that's remnant at 26 north, and that's this shown in the green curve. It's very small and not really very variable. And then we have the deep western boundary currents. So we've divided into 1,100 to 3,000 meters depth. We call that the upper North Atlantic deep water, or the Labrador seawater component. And then below 3,000 meters, that's in the dark blue curve, that's the flow southward of lower North Atlantic deep water. That's the water that's formed north of Iceland. That's why we chose those depths to break it up. Now you can see quite wild variability, particularly in the lower North Atlantic deep water. In fact, one of the surprising findings was that we saw it actually stopped. The southward flow of lower North Atlantic deep water actually stopped for about 10 days there in October 2004. So the level of this variability is quite surprising. And you have to put this in the framework of most oceanography in the past has gone out in a particular week or month and made some measurements, and then has, as I was trying to show you in the beginning, to find they find the deep western boundary current, they estimate the transport, and they say the transport of the deep western boundary current is 7 stardrops, and then that becomes written up into a series of papers. What we see here is, 1 week it might have been 2 stardrops, and 1 week it might have been 15 or 20 stardrops. So it can vary from week to week, and we're trying to measure the variability over time. And the key, of course, is that we're trying to measure the variability on interannual timescales to see if the overturning circulation is changing over time. Now, we put we make these measurements. There are 2 cruises each year. We generally deploy the western boundary array on a relatively short cruise, so this array, in about 10-day cruise operating out of either the Bahamas or Miami, because it's quite convenient. You can do all that work quite easily there. And then we have a longer cruise in the autumn that usually starts from the Canary Islands and goes out and does the eastern moorings, but also goes to the Mid-Atlantic Ridge. So that tends to be about a 30-day cruise to go out and monitor. And so we are operating 2 cruises, 2 operational rapid cruises each year. We pick up the instruments, and then, of course, with 200 instruments, it's quite a major job to process them. The goal is that we put the measurements into the British Oceanographic Data Centre, BODC, and we try to put them up on the web so that you can look at them. So if you would like to look at some of the rapid measurements, there is a website here in Southampton that you can quite easily find. And so this is a time series that we're presently dealing with. It's a 5-year time series of what the variability is on a kind of a 10-day scale. So we've averaged it down to 10 days. And the blue is the Gulf Stream transport. The magenta here is the mid-ocean. This is the southward recirculating water. The black is the Ekman, and then so this shows the upper level components, and this is the net northward flow of warm water, which we call the MOC, and you can see the variability here. Quite a large amount of variability, although they have well-defined means. If we look at the statistics, again, we've got a Gulf Stream transport of about 32. This is over the 5 years measurement. The Ekman is 3.6, and the recirculation is about 17. And so in the net, we have a mean or a time average meridional overturning circulation of about 18 stardrops. And again, we look at the standard deviations. These 3 components appear to us to be independent. That is, there's no correlation between Gulf Stream, Ekman, and mid-ocean recirculation at the moment. And so they have similar standard deviations, these 3 components. So our standard deviation, or the variability in the meridional overturning circulation, has a standard deviation of about 4.7, almost 5 stardrops. Now we're also interested in trends. You always get a trend in the circulation. None of the trends are statistically significant at the moment. You might say that just by looking. You don't see this red curve. You can't detect a trend. I always say, if you see a trend with your eye, then there probably is a trend, statistically speaking. And if you can't see one, then there's probably not a trend, statistically speaking. So I don't think any of us see a distinct trend. in the components. But basically, we calculate them anyway. And so if we look at the overturning circulation, there's only a very small trend towards a slowdown. That's over 5 years, but not anything statistically reliable. So we continue to monitor the overturning circulation. We proposed this in the beginning as a kind of a feasibility project. There were major critics around the world who said we couldn't monitor the overturning circulation. But we convinced the funding agencies that they should at least give us a try. So we were initially funded for 4 years, from 2004 to 2008. Based on the kind of first year's result, we established that the monitoring system did work. We showed that we could independently measure 5 components of the circulation, and that show that they added up to give a mass balance, which for us indicated that the mooring system worked. There were no assumptions that had to be made for the monitoring. And we convinced then National Science Foundation, NOAA, and NERC to achieve a decade of observations. So we're presently funded to continue for 10 years till 2014. And at the moment, we're preparing in January 2012. We're going to have an international review at which we're going to make a case for continuing the rapid observations on a sustained basis. Probably we are going to have to reduce the size of the arrays, and everyone wants cost cuttings. But we're presently trying to make the case for the observations. Now, so the circulation, my summary of the talk is really that the circulation of the North Atlantic Ocean has profound effects on climate. In particular, the ocean warms the cold westerly winds that come from North America in winter, so they arrive in Europe with much warmer temperatures. We've developed a unique monitoring array at 26 degrees north to provide an early warning system to changes in the Atlantic overturning. Based on the rapid measurements, we think we can estimate the year-long average overturning with an error of 1.5 starters, which is about 7% of the signal. And at the moment, we think we've got a 7-year time series. We're now examining climate events, large fluctuations in circulation and heat and freshwater transports, and their connections with other climate variables. Now, I think one of the things is that we now, with this array, on a kind of a personal note, I was thinking this time series looked a bit dull, this 5-year time series. So up until the summer, I was thinking, well, it's same old, we might say. It's looking variable, but pretty regular. In the winter of 2000, the end of 2009, and then again in the winter of 2010, we have had major events where the overturning circulation has reduced by about nearly 25%. And so we're presently not got the time series up on the website yet. We've had we basically got another 18 months of data measurements back and processed that we started processing in the summer. But there are big events that we can see, and there's just a small residual problem in the data. But we're expecting to put the time series that go through December 2010 up on the website in the next within the next 2 weeks. And so I encourage you to look at the website and see what the variability is. We had 2 cold winters in Britain in December 2010, and then also in December 2011. And what we're trying now to establish, of course, which is of interest to the to society and the politicians, is whether the ocean circulation had anything to do with these cold winters. In particular, whether the overturning circulation was, a driver of these changes. So that's the kind of problems that we're working on. We're not trying to we're not trying to hold on to the data. We'd like everybody to use it. I think it's possibly a good potential data set that you don't have to ask for permission. You just go to the website and you download the data you want. And it possibly makes an interesting project for master's student theses, maybe even a PhD thesis. So thank you very much for coming to listen to this talk about subtropical ocean circulation in the North Atlantic and what we're doing to monitor on a continuous basis.
Okay, thank you very much.